Hello and welcome to Science for Bedtime. This is a place where science can move slowly without pressure, and where your attention is allowed to come and go. If this channel has become part of your evenings, you're warmly welcome to support it by liking the video or subscribing. It helps these quiet science stories continue gently and consistently for anyone who might be looking for them. Somewhere in the universe, there are objects we rarely see directly but often notice through what they change. They do not announce themselves with bright surfaces or crisp outlines. Instead, they leave patterns in the motion of stars. They leave arcs in passing light. They leave warmth in spiraling gas. In those patterns, we begin to sense a kind of presence that is both simple and extreme. Black holes are sometimes described as emptiness, like holes cut out of space. But the more accurate picture is almost the opposite. A black hole is not an absence of reality. It is a region where gravity becomes so concentrated that the usual paths outward no longer exist. It is a place where the universe still has mass, still has influence, but where the influence becomes sealed behind a boundary. One of the calm surprises of astronomy is that we can study black holes without ever seeing a black object in the usual way. In practice, we often find them by watching something else. A star moves in an orbit that seems to circle nothing visible. A stream of gas heats up to a fierce glow and then disappears. A galaxy's center behaves as if a heavy anchor is holding it together. In each case, the black hole is inferred, like a hidden weight revealed by the way a pendulum swings. The idea of a black hole begins with a simple notion: escape. To leave a planet, a rocket must reach a certain speed. It must climb out of the planet's gravitational field. That requirement is not arbitrary. It comes from how gravity shapes energy and motion. For small bodies like asteroids, escape is easy. For planets, it is harder. For stars, harder still. If enough mass is packed into a small enough region, the escape speed rises until it reaches the speed of light. This escape speed picture is a useful intuition. In full general relativity, the horizon is defined more precisely as a causal boundary in spacetime. Light is not a thing that can slow down to escape more carefully. In our best current understanding, in empty space, light always moves at the same speed. That means there is a threshold where escaping stops being an option, not only for spacecraft or atoms, but for light itself. When the escape speed at a particular boundary reaches the speed of light, that boundary becomes special. It marks the edge of a region that cannot send signals outward. That edge is called the event horizon. It is not a wall made of material. It is not a crust you could scrape or a surface you could stand on. It is a boundary defined by what can influence what. Outside it, signals can travel outward and reach distant places. Inside it, every possible future path stays inward. The universe beyond the boundary can continue normally, but it cannot receive news from within. It can help to picture this boundary in a very practical way. Imagine you are on a shoreline at night, and you can see a lighthouse far away. As long as the light reaches you, you are connected to that lighthouse, even if only by a thin line of information. If the light can no longer reach you, the lighthouse may still exist, but it has left your world. The event horizon is like the moment when outward light can no longer make it back. What's inside does not vanish from reality. It simply becomes unreachable. The phrase event horizon sounds dramatic, but its meaning is quiet. It is a limit on communication. It is a boundary for cause and effect. From far away, a black hole can be remarkably ordinary in one sense. If you replaced the Sun with a black hole of the same mass, the planets would still follow nearly the same orbits. The gravitational pull at a distance would be much the same. What changes is not the distant influence. What changes is the existence of a region where the geometry becomes so steep that escape is no longer part of the map. That word, geometry, matters here. In modern physics, gravity is not only a force tugging on objects. In Einstein's general theory of relativity, gravity is tied to the shape of space-time itself. Mass and energy influence the structure of space-time, and that structure influences how matter and light move. Objects follow the natural, straightest paths available to them, but those paths can bend when space-time is curved. In everyday life, space feels like a simple stage. Time feels like a steady flow. In strong gravity, those feelings become less reliable. Clocks can tick at different rates, depending on how deep they sit in a gravitational field. Light can change its frequency as it climbs out of gravity, stretching toward redder wavelengths. These are not poetic ideas. They are measurable effects, seen even in weaker gravity near Earth, and accounted for in technologies like GPS. Near a black hole, those same effects become dramatic. The closer a signal is emitted to the event horizon, the harder it is for that signal to reach far away without losing energy. Light climbing out of deep gravity becomes increasingly redshifted. To a distant observer, signals from near the horizon can appear slowed and weakened, as though time itself is being smeared into a long, quiet fade. The object producing the light does not necessarily feel its own time slowing. Locally, its clock can tick normally. The difference comes from how different regions of curved space-time compare their measurements. This difference in perspective is one of the gentlest oddities in black hole physics. From far away, an infalling object can appear to approach the horizon more and more slowly. Its light grows redder, dimmer, and harder to detect. In many simplified descriptions, it never quite seems to cross. Yet in the infalling object's own experience, the crossing can happen in a finite time without a special jolt at the boundary. Both descriptions are ways of talking about a single reality, viewed through different choices of timekeeping. The event horizon is also where black holes become easy to misunderstand. People sometimes imagine it as a place of immediate destruction. That is not always the case. The severity of the tidal forces at the horizon depends strongly on the black hole's mass. In smaller black holes, the change in gravity across a human-sized distance can be enormous near the horizon, stretching and squeezing intensely. In very massive black holes, the horizon can be so large that the local curvature there is comparatively gentle. The truly extreme tides become unavoidable deeper in. Tidal forces are the same general effect that raises ocean tides on Earth. Gravity is slightly stronger on the near side of a body than on the far side. That difference stretches objects along the direction of gravity and compresses them sideways. Near a black hole, the gradient of gravity can become intense. The stretching can be strong enough to pull apart stars, turning them into long streams of hot gas. When a star is torn this way, the process can produce a bright flare as the shredded material heats and spirals inward. Even without seeing the black hole, we can see the feeding. Feeding is one of the main ways black holes become visible indirectly. A black hole itself does not shine like a star, but matter falling toward it can become extraordinarily luminous before crossing the horizon. Gas rarely falls straight in. It tends to swirl because it carries angular momentum like water circling a drain. That swirling can form an accretion disk, a flattened structure where material orbits, collides, and heats up. Friction and turbulence in the disk turn gravitational energy into heat and light. In some environments, this light can be intense. The inner regions of a disk can glow in X-rays produced by matter heated to extreme temperatures. Sometimes magnetic fields in the disk can help launch narrow jets of particles outward along the black hole's rotation axis. These jets can travel vast distances and influence the surrounding galaxy. In those cases, a black hole is hidden at the center, but its environment becomes a loud messenger. There is something reassuring in that pattern. Even when an object is fundamentally dark, nature still leaves clues. The universe is not obligated to show us everything directly, but it often allows us to learn through influence. Orbits, heat, light, bending, ripples in spacetime. A black hole becomes an example of how astronomy works at its best, careful inference, built from many small pieces that agree. Light bending is another piece. Gravity can curve the path of light. This effect, gravitational lensing, can make background objects appear distorted, magnified, or duplicated. In everyday gravity, the effect is small. On cosmic scales, it becomes a tool. Clusters of galaxies can act like lenses, individual stars can act like lenses, and a black hole, with its concentrated mass, can act like an especially sharp lens near its boundary, causing light to loop around or skim past in tight arcs. Close to a black hole, there are special orbits for light itself. Photons can, in principle, circle a black hole at certain radii, though these orbits are unstable. A small disturbance sends the light either outward or inward. This delicate behavior contributes to the appearance of a black hole's shadow, the dark region in the center of a bright ring seen in some images of black hole environments. That shadow is not the horizon itself. It is a projection of the region from which light cannot easily reach us, shaped by the bending of light around the black hole. In recent years, humanity has begun to capture images that are not photographs in the usual sense, but reconstructions built from many radio telescopes working together. By combining telescopes across Earth into a virtual dish the size of the planet, scientists have produced images of the bright ring of hot gas around a supermassive black hole with a central dark region consistent with the expected shadow. This kind of observation does not reveal what lies inside, but it strengthens the case that the geometry we predict is showing up in the sky. Black holes come in more than one scale. Some form from the collapse of massive stars, leaving behind objects with masses a few times that of the Sun. These are often called stellar mass black holes. They can exist quietly, detectable mainly when they interact with a companion star or surrounding gas. In binary systems, a black hole can pull material from a partner star, creating an accretion disk and emitting X-rays. Watching those X-rays and the companion's orbit gives us a way to estimate the unseen mass. At the other extreme are supermassive black holes found at the centers of many galaxies. These can have masses millions or billions of times the Sun's. Their presence is suggested by the rapid orbits of stars near galactic centers and by the enormous energy output of active galactic nuclei and quasars. In our own galaxy, the motions of stars near the center point to a compact, massive object consistent with a supermassive black hole. Again, the black hole is not seen as a dark ball, it is seen as a gravitational organizer. Between these two categories, astronomers also discuss intermediate mass black holes, which may exist in some dense star clusters or special environments. Evidence for them is still being refined. Their origin is an open question in astrophysics. They could form from repeated mergers of smaller black holes. They could form from the collapse of unusually massive stars in early conditions, or they could form through other pathways we do not yet fully understand. Here, uncertainty is part of the story, and it's allowed to remain. Formation is where black holes connect most intimately with the life of stars. A massive star spends much of its life balancing two tendencies. Gravity pulls inward, pressure from hot gas and nuclear fusion pushes outward. As long as fusion in the core continues to release energy, the star can remain stable. Over time, stars change their fuel. They build heavier elements. In very massive stars, this can proceed through several stages, each one shorter than the last. Eventually, the star's core can reach a point where it can no longer gain energy from further fusion in the same way. When the outward pressure weakens, gravity wins, the core collapses. In many cases, this collapse triggers a supernova, an explosion that can briefly outshine whole galaxies. The outer layers are expelled into space, enriching the cosmos with elements forged in the star's lifetime and death. What remains at the center depends on how much mass is left behind. If the remnant is light enough, it can settle into a neutron star, supported by quantum effects and the behavior of matter at nuclear densities. If the remnant is heavy enough, those supports may not be sufficient. The collapse can continue past the point where any known pressure can halt it. In that case, an event horizon forms and a black hole is born. It is worth pausing on the quietness of that end. The phrase black hole can feel violent. Yet in many descriptions, the defining moment is not an explosion, but a crossing of a threshold. A boundary forms where escape is no longer possible. From that point, the object's future is sealed inward. The outside world may see aftermath, a supernova remnant, a fading glow, an empty spot where a star once was. But the black hole itself is defined by the boundary, not by fireworks. Once a black hole exists, it can grow. It can gain mass by accreting gas and dust. It can swallow stars that wander too close. It can merge with other black holes. Mergers are especially important because they lead us to another kind of evidence: gravitational waves. Gravitational waves are ripples in spacetime produced when massive objects accelerate in certain ways. They were predicted by general relativity and later detected directly with sensitive instruments that can measure changes far smaller than the width of an atom over long distances. When two black holes spiral toward each other and merge, they can release a burst of gravitational waves. These waves carry information about the masses and spins of the black holes and about the final object formed. This means black holes, while dark in light, can be heard, in a sense, through the stretching and squeezing of spacetime itself. The signal is not sound traveling through air. It is a pattern in the geometry of space, arriving at Earth after traveling across the universe. The thought is calm and slightly astonishing. Even when no light is involved, the universe can still send a message. Many black holes also spin. Rotation is common in astrophysics because stars and gas clouds carry angular momentum. When something collapses, it often spins faster, like a figure skater drawing in their arms. A spinning black hole is described by a family of solutions in general relativity that differ from the simplest non-spinning case. Spin changes the structure of the space around the black hole and can create regions where spacetime is dragged along with the rotation, an effect known as frame dragging. In the vicinity of strong rotation, the idea of standing still becomes complicated. There can be regions outside the horizon where an object cannot remain stationary relative to distant stars because spacetime itself is being pulled around. This does not mean the black hole is throwing out material from inside. It means the geometry around it is dynamic. Rotation becomes part of the landscape, shaping what paths are possible. Spin matters for what we observe. It influences how close matter in an accretion disk can orbit before plunging inward. It affects the efficiency with which accretion can convert falling matter into radiation. It can help shape the conditions that launch jets. In this way, a black hole's most important traits from the outside can be remarkably few, yet those few traits can sculpt large environments. There is a compact way physicists sometimes describe this. From far away, black holes can be characterized by mass, spin, and electric charge. In real astrophysical settings, charge is usually expected to be small because a significant imbalance would tend to attract opposite charges and neutralize. Mass and spin are the stars of the show. They are enough to govern orbits, lensing, and the behavior of matter near the horizon. And yet there is a deeper question that quietly waits behind these ideas. If a star collapses, it has an intricate internal structure. It has composition, patterns, histories. If it becomes a black hole that can be described from outside by only a few numbers, what happens to the rest of the detail? Is it hidden? Is it transformed? Does it remain in a form the universe still knows, even if we cannot access it? This question leads into one of the most famous puzzles in black hole physics, sometimes called the information paradox. It sits at the boundary between general relativity and quantum mechanics, our two deepest and most successful frameworks. Relativity describes gravity and spacetime on large scales. Quantum mechanics describes matter and information on small scales. Each works extremely well where it has been tested, but black holes seem to invite both theories into the same room, and the conversation becomes complicated. There is a remarkable result associated with that conversation. Black holes may not be perfectly black. In quantum theory, empty space is not truly empty. It has fluctuations. Fields can briefly form particle-like excitations. Near a horizon, those fluctuations can interact with the curved geometry in a way that, in simplified terms, allows a faint emission of radiation to escape. This is known as Hawking radiation, after Stephen Hawking, who described the effect in the 1970s. Hawking radiation is not like a beam shining from inside the black hole. It is associated with quantum fields in the region near the horizon. The result is subtle. For stellar mass black holes, the predicted temperature is extremely low, and the radiation would be extraordinarily difficult to detect directly. For much larger black holes, it is even colder. But the theoretical implication is gentle and profound. If black holes can radiate, then over very long times they can lose mass. They can, in principle, evaporate. If that is true, a new question appears naturally. If a black hole can slowly fade away through radiation, what happens to the information about what fell in? In many versions of quantum theory, information is not supposed to be destroyed. It can be scrambled, spread out, and made hard to reconstruct, but not erased from the universe's accounting. Hawking's early calculations suggested the radiation might be thermal, carrying no detailed imprint. That would imply information could be lost, which would be a major shift in physics. This is one of those moments where we can be honest about the state of knowledge. Physicists have made progress, and there are strong reasons many now suspect information is preserved in some way, perhaps encoded in correlations within the radiation, perhaps stored at the horizon in a holographic description, perhaps revealed by a theory of quantum gravity we do not yet fully possess. But there is still no single, universally accepted picture that has been confirmed by direct observation. The uncertainty is real, and it is part of what makes black holes such a steady source of curiosity. For our purposes here, it's enough to hold the feeling of the boundary. Black holes sit at edges, the edge of escape, the edge of visibility, and in some sense, the edge of what our current theories can comfortably explain together. That does not mean the story becomes chaotic. It means the story becomes open, like a quiet question left on a table. In the night sky, black holes are not rare in principle, but they are often quiet. Many do not feed brightly. Many drift through the galaxy without dramatic effects. Some may be isolated remnants of old stars moving among clouds and faint starlight. Others may lurk in dense environments where gas and stars provide a steady supply of matter. Some may be the engines of active galaxies, shaping the growth of stars through the energy they release around them. And in all cases, the same simple boundary remains: a horizon defined by geometry and by limits on what can send news outward, a gravitational influence that persists even when the interior is hidden. This combination of simplicity and mystery is part of why black holes fit naturally into a slow science narration. There is a clear foundation, there is a calm explanation, and there is room for gentle expansion without needing to force a conclusion too quickly. Black holes also remind us of something practical about knowledge. We do not need to know everything to know something. We can measure orbits and infer mass. We can model disks and infer spin. We can detect ripples and infer mergers. We can image a shadow and infer a horizon-like structure. The interior remains a question, but the outer facts are real, tested, and surprisingly consistent across many lines of evidence. So the topic settles into place as a kind of quiet landscape. There is a boundary where light cannot return. There are regions where time and frequency shift in measurable ways. There are star deaths that can lead to horizons forming. There are galaxies whose centers behave as if something massive and compact is sitting there. There are ripples in space-time that arrive on Earth, carrying the signature of black holes meeting in the dark. And there is also the simple human feeling of looking at a concept that is both understandable and strange. A black hole is not a monster in the sky. It is a consequence of how gravity behaves when mass becomes concentrated. It is an object in the sense that it has measurable properties. It is a region in the sense that it is defined by boundaries and geometry. It is quiet in the sense that it does not shine on its own. And it is powerful in the sense that it can reshape matter and motion around it. Inside the event horizon, the structure of space-time becomes more unfamiliar. The distinction between directions changes. Outside, it is possible to choose paths that lead outward or inward. Inside, every future-directed path leads deeper. This is not because of a force pushing inward, but because of how time and space are arranged. The inward direction becomes tied to the passage of time itself. This is one of the reasons black holes are so difficult to picture with everyday intuition. Our experience is built in regions where space-time is only gently curved. Inside a black hole, the geometry is extreme. Concepts like standing still or turning around lose their usual meaning. Yet even here, the description remains grounded in geometry rather than drama. Deeper still lies what classical physics calls a singularity. This term does not describe a solid object or a physical surface. It describes a limit of the equations, a place where quantities like density and curvature grow without bound. In such regions, the mathematical tools of general relativity signal that they are no longer sufficient. The theory is pointing to its own edge. Physicists do not treat singularities as settled physical facts in the same way they treat horizons or orbits. Instead, they are often seen as signs that a more complete theory is needed. Just as classical physics breaks down at atomic scales and must be replaced by quantum mechanics, general relativity is expected to be replaced or extended in regions of extreme curvature. What actually happens at the deepest interior of a black hole remains uncertain. This uncertainty does not weaken what we know, it clarifies it. The horizon, the exterior geometry, the influence on surrounding matter, and the production of gravitational waves are all well supported by evidence. The interior beyond the horizon is hidden by design, sealed off from direct observation. Nature has drawn a line there, not as a puzzle to frustrate us, but as a boundary of causal connection. In that sense, black holes are not violations of the universe's rules. They are consequences of those rules carried to their extremes. Gravity continues to do what it always does. Mass continues to curve space-time. Light continues to follow the available paths. When those paths all lead inward, a black hole appears. It is also important to remember that black holes do not roam the universe, consuming everything around them. Their influence weakens with distance, just like any gravitational field. A black hole is dangerous only if you approach it closely, just as a star or planet is dangerous only if you come too near. On galactic scales, black holes are more like anchors than predators. In galaxies, stars orbit the center according to gravity, not fear. Even near a supermassive black hole, many stars can follow stable paths for millions of years. The danger zone is confined to the immediate neighborhood of the horizon. Beyond that, the black hole's presence blends into the larger gravitational structure of the galaxy. This quiet coexistence is part of why black holes can sit at the centers of galaxies without tearing them apart. They grow, but they also regulate. Energy released by accretion can heat surrounding gas, slowing the formation of new stars. Over time, this feedback helps shape the size and structure of galaxies. The black hole and the galaxy evolve together, linked but not locked in conflict. The story of black holes is also a story of detection. For much of the 20th century, black holes were theoretical solutions, mathematical possibilities within Einstein's equations. Over time, evidence accumulated through indirect signs, unusual X-ray sources, rapid stellar motions, energetic galactic nuclei. Each piece alone suggested something compact and massive. Together they formed a consistent picture. The detection of gravitational waves added a new sense to astronomy. Instead of relying only on light, scientists can now listen to changes in space-time itself. Black hole mergers produce distinctive waveforms that encode information about the masses and spins involved. When detectors capture these signals, they confirm not only the existence of black holes, but the dynamic behavior of space-time under extreme conditions. These observations also show that black holes are not static relics. They interact, merge, and grow. Over cosmic history, smaller black holes can combine into larger ones. This process likely contributes to the formation of the supermassive black holes seen at galactic centers today. The universe builds complexity not just through matter, but through geometry in motion. Despite their dramatic reputation, black holes are woven smoothly into the cosmic fabric. They are endpoints of stellar evolution, participants in galactic growth, and testbeds for fundamental physics. They do not stand apart from the universe. They arise from it, obeying its rules, even as they push those rules to their limits. There is a steady comfort in that realization. The most extreme objects we know are not exceptions thrown in for spectacle. They are natural outcomes of simple principles applied over vast scales. Gravity pulls, space curves, light follows paths. Time compares itself differently depending on depth. When mass concentrates enough, a boundary forms. Nothing mystical is required. And so when black holes enter the quiet landscape of nighttime science, they do not demand awe through violence or fear. They invite a slower kind of attention, an attention that rests on structure rather than spectacle, on boundaries rather than catastrophes, on the calm logic of a universe that continues to behave consistently even in its most extreme corners. In that calm logic, there is room to linger without urgency, to let the idea of curved space settle gently, to let the image of a dark center surrounded by light form without strain, to allow questions to remain open without needing to be solved immediately. The black hole does not rush us. It simply exists, shaping what passes nearby and remaining silent about what lies beyond its edge. There is another way black holes may enter the universe, one that does not rely on stars at all. In the very early moments after the universe began expanding, conditions were far denser and more uneven than they are now. Small variations in density may have existed, regions where matter was packed slightly more tightly than average. In some theoretical models, these regions could have collapsed directly under their own gravity, forming black holes long before the first stars ever ignited. These hypothetical objects are known as primordial black holes. They are different not because gravity behaves differently, but because their origin is different. Instead of forming from stellar collapse, they would form from the universe itself, shaped by the conditions present in its earliest phases. Their possible sizes span a wide range, from very small to very large, depending on when and how they formed. Whether primordial black holes exist in significant numbers remains uncertain. Astronomers search for their signatures indirectly, looking for subtle gravitational effects. One method involves watching distant stars for brief changes in brightness caused by gravitational microlensing. If a compact, dark object passes in front of a star, its gravity can focus the star's light, producing a temporary brightening. By studying these events carefully, scientists can place limits on how many unseen massive objects might be drifting through space. Primordial black holes are also discussed in connection with dark matter, the unseen mass that appears to make up much of the universe's matter content. Some models explore whether a portion of dark matter could consist of black holes that formed early and remain difficult to detect. So far, observations have constrained this idea strongly, but not completely ruled it out. The possibility remains open, quiet, and tentative. These early formed black holes, if they exist, would have experienced a very different environment from those born from stars. They would have been immersed in a hot, dense universe filled with radiation and particles. Over time, as the universe expanded and cooled, they would drift into calmer cosmic eras. Their long-term behavior would still follow the same gravitational rules, but their histories would carry the imprint of a much younger cosmos. Thinking about primordial black holes gently shifts the perspective. Black holes are no longer only the remnants of stellar lives, they become potential fossils of the universe's earliest structure, records of how matter and gravity behaved when everything was closer together. Whether or not these objects are real in abundance, the idea itself reflects how black holes connect cosmology and gravity into a single conversation. When two black holes orbit one another, their motion is not perfectly silent. They lose energy through gravitational radiation, slowly spiraling inward. This loss is extremely small at large separations, but as the orbit tightens, the emission grows stronger. The final moments of inspiral and merger release a burst of gravitational waves that propagate outward, carrying a precise record of the system's dynamics. The detection of these waves has transformed black holes from inferred objects into directly observed participants in cosmic events. Each detection confirms that spacetime itself can vibrate and transmit information. The signals do not tell us about surfaces or interiors, they tell us about mass, motion, and geometry. They confirm that black holes behave exactly as predicted by general relativity, even under extreme conditions. After two black holes merge, the resulting object is not immediately quiet. It rings. The newly formed black hole settles into a stable state by emitting gravitational waves in characteristic patterns, often described as a ringing tone that fades with time. This process, sometimes called ringdown, reflects how space-time around the black hole adjusts to a new configuration. The simplicity of the final state is striking. Complexity collapses into a few defining traits. These mergers also teach us something subtle about energy. Not all of the mass energy of the original black holes remains locked in the final one. A portion is carried away by gravitational waves, radiated across the universe. This is not destruction, it is transformation. Energy changes form, leaving behind a quieter but heavier remnant. Across billions of years, repeated mergers may help explain how some black holes grew so large. Small beginnings accumulate through encounters and feeding, gradually building the giants found at galactic centers. This growth does not require a single dramatic origin. It unfolds through steady, patient processes that mirror the universe's overall rhythm. Supermassive black holes, despite their name, are not dense in the everyday sense. Their enormous mass is spread across a vast horizon. For these giants, the curvature of spacetime at the horizon can be gentle enough that a falling object might not experience extreme forces there. The most intense effects wait deeper inside. This counterintuitive calm at the edge highlights again how size and density are not the same thing. The presence of supermassive black holes at galactic centers raises an important question about timing. Observations show that some of these giants existed when the universe was relatively young. Explaining how they grew so quickly challenges simple models of slow accretion. This has led to ideas involving direct collapse of large gas clouds, rapid early feeding, or early mergers. Each possibility reflects ongoing research rather than settled fact. What remains clear is that galaxies and their central black holes evolve together. The growth of one influences the growth of the other. Gas flowing inward can feed both star formation and the black hole. Energy released near the center can heat or expel gas, altering future star formation. Over long timescales, this feedback creates a balance, shaping the structure of galaxies across the universe. This mutual influence suggests that black holes are not merely passengers in cosmic history. They participate actively, not through intent, but through physics. Gravity and energy exchange are enough. No additional agency is required. The laws of nature, applied consistently, produce structures that shape their surroundings over immense distances. Beyond growth and mergers, black holes also invite deeper reflection about entropy and order. In physics, entropy is a measure of how many microscopic configurations correspond to a macroscopic state. It is often associated with disorder, but more precisely, it is related to the amount of information needed to specify a system's microscopic state. Black holes, despite appearing simple from the outside, are associated with enormous entropy, proportional to the area of their horizons. This connection between horizon area and entropy was one of the great insights of 20th century theoretical physics. It suggests that black holes are not merely geometric oddities. They obey thermodynamic-like laws. Their mass relates to energy. Their horizon area behaves like entropy. Their surface gravity relates to temperature. These parallels are not metaphors, they are precise mathematical relationships. What makes this remarkable is that the entropy seems to reside not in a volume, but on a surface. This hints at a deeper principle sometimes called holography, where information about a region may be encoded on its boundary. While this idea remains under active investigation, it has influenced thinking across quantum gravity, string theory, and cosmology. The notion that information might be tied to surfaces rather than interiors changes how we imagine space itself. It suggests that what we experience as three-dimensional space may emerge from more fundamental relationships. In this view, the event horizon becomes more than a boundary of escape. It becomes a bookkeeping surface for information, quietly storing correlations beyond direct reach. These ideas remain theoretical, but they are grounded in careful reasoning rather than speculation. They arise from trying to reconcile gravity with quantum principles. Black holes serve as testing grounds for these attempts because they bring extreme gravity and quantum effects into close proximity. The questions they raise are not about distant curiosities, they are about the foundations of physical law. Despite this depth, it is not necessary to hold every detail in mind. The broader picture is gentle. Black holes are places where familiar ideas stretch. Time compares itself differently. Light follows curved paths. Information raises new questions. And yet the universe continues to behave coherently. There is no collapse into contradiction, only an invitation to refine understanding. From an observational standpoint, much of what we know continues to come from patient measurement. Astronomers track stellar motions near galactic centers. They monitor X-ray emissions from accretion disks. They record gravitational wave events as detectors grow more sensitive. Each new observation narrows uncertainty, filling in part of the landscape while leaving room for mystery. This balance between knowledge and openness is a defining feature of black hole science. Some aspects are robust and well-tested, others remain speculative. Both coexist without tension. The unknown is not a failure, it is a boundary, much like the horizon itself, marking where current tools reach their limit. It can be helpful to let the idea of boundaries rest quietly. Boundaries are not always barriers. They can be places of transition, where one description gives way to another. In black holes, the boundary is physical and causal. In theory, it is also conceptual, guiding where one framework must eventually connect to another. In the night sky, black holes do not stand out as dark circles. They blend into the larger structure of galaxies and clusters. Their presence is felt through motion and energy rather than appearance. This invisibility is not a flaw. It is a reminder that much of the universe operates beyond direct sight, yet remains accessible through careful inference. The calmness of this process mirrors the calmness of the objects themselves. Black holes do not chase, they do not hunt. They respond to what comes near. Matter follows paths shaped by gravity. Energy transforms according to consistent rules. Over time, structures grow, interact, and settle. As this picture continues to unfold, it does not demand alert attention. It allows a softer awareness, a sense of large scales moving slowly, of deep time unfolding without urgency, of extreme objects fitting naturally into a universe governed by steady principles. Black holes, in this light, become less like dramatic endings and more like quiet continuations. They are not interruptions in the cosmic story, they are chapters written in a different geometry, following the same grammar of physics. And, as with many deep ideas, they do not need to be grasped all at once. They can remain gently present, shaping thought without pressing for resolution. As black holes remain present over immense spans of time, another slow process becomes relevant, one that unfolds far beyond human timescales. Even the most massive and seemingly permanent objects are not exempt from change. On the longest scales we can imagine, black holes participate in the gradual evolution of the universe itself. If this slow emission continues uninterrupted over unimaginable lengths of time, a black hole would gradually lose mass. The process would be almost imperceptible at first, stretching across spans far longer than the current age of the universe. But given enough time, even the largest black holes would slowly shrink. This idea reframes black holes not as eternal endpoints, but as participants in a very long story of transformation. What happens at the final stages of such an evolution is still uncertain. The physics involved lies at the intersection of gravity and quantum mechanics, a regime we do not yet fully understand. Some models suggest a quiet fade, others allow for a final release of energy. What matters here is not the specific outcome, but the broader implication. Black holes, like stars and galaxies, may have life cycles, even if those cycles are far longer than any familiar clock. This perspective places black holes within the wider context of cosmic time. The universe itself is changing, it is expanding, galaxies drift apart, star formation slows as gas becomes scarce. Over extremely long periods, the bright era of stars gives way to darker ages dominated by stellar remnants. Black holes remain as some of the last massive structures, quietly shaping what little activity remains. In such distant futures, black holes would become increasingly isolated. Without nearby matter to feed on, they would grow quiet. Their surroundings would thin. Their interactions would become rare. Gravity would still act, but with fewer partners to influence. The universe would stretch larger and cooler, carrying black holes along in its expansion. These ideas are not predictions in the everyday sense. They are extensions of known principles into regimes we cannot test directly. They help frame black holes not as anomalies, but as elements of a universe that continues to evolve, even when change becomes subtle and slow. Throughout this long arc, one feature remains constant. Black holes are defined by boundaries, boundaries of escape, boundaries of visibility, boundaries of what can be known directly. These boundaries are not arbitrary. They arise naturally from the behavior of gravity when mass becomes concentrated. They are not added by hand. They emerge. It is this emergence that makes black holes feel both natural and strange. They are not exotic intrusions into physics. They are solutions to its equations. And yet they carry those equations into unfamiliar territory where time stretches, light bends sharply, and information raises questions that reach beyond current understanding. In the quiet context of nighttime listening, black holes offer something steady rather than dramatic. They invite a sense of scale, not just spatial scale, but temporal scale. They remind us that the universe operates comfortably across ranges far larger than any individual experience. Processes that feel frozen or permanent to us may be temporary on cosmic timelines. They also remind us that not everything needs to be illuminated to be meaningful. Much of what shapes the universe does so invisibly. Gravity itself is not seen, it is inferred. Black holes simply take that principle to an extreme, shaping space without revealing their interiors. When astronomers point telescopes toward the sky, they do not search for darkness itself. They search for motion, for energy, for subtle distortions. From these, they reconstruct the presence of objects that cannot be photographed in the usual way. This patient reconstruction mirrors the way understanding itself often works, built from indirect clues gathered over time. In that sense, black holes fit naturally into a calm scientific narrative. They do not require urgency, they do not demand resolution, they allow space for uncertainty without discomfort. Some questions remain open, some details are still debated. This openness is not a flaw, it is part of how science stays alive. The most important facts remain stable. Gravity curves spacetime. Mass concentration can create horizons. Light follows the available geometry. Time compares itself differently in strong gravity. Black holes influence their surroundings through well-understood mechanisms. These foundations are solid, even as deeper questions continue to be explored. And beyond the equations and observations, there is the quieter human response. The recognition that the universe contains regions we cannot access, not because of technological limits, but because of how reality itself is structured. This recognition does not diminish understanding, it frames it. Black holes show us that the universe is not obligated to be fully transparent. Some regions are hidden not by choice, but by consequence. And yet even hidden regions leave traces. They shape orbits, they guide flows of gas, they ripple space-time, they remain part of the story, even when unseen. As this long view settles, it becomes easier to let details soften, to allow the image of a dark center surrounded by motion to remain without strain, to accept that some boundaries are not meant to be crossed, only approached conceptually. The universe does not hurry us toward answers, it unfolds at its own pace. Black holes, among the slowest and most patient objects we know, embody that rhythm. They persist, they influence, they change quietly over spans that dwarf human history. And in that patience there is a certain calm, a sense that even the most extreme phenomena fit within an ordered whole. Nothing here is arbitrary, nothing is rushed. Gravity does what it does, space-time responds, matter follows, time flows according to where it finds itself. So as this quiet exploration comes to rest, there is no need to conclude with a summary or a lesson. The ideas can remain as they are, present but unforced, known but not exhausted. Black holes continue to exist, scattered across the universe, silent and influential, shaping paths without revealing their cause. They are not endings, they are regions, they are not voids, they are structures, they are not disruptions, they are outcomes. And within the calm consistency of the universe, they remain exactly where gravity and time place them. Good night.